So this is example 24.2, and it deals with this parallel plate capacitor system here, where we have some positive charge plate on the top and a negative charge plate on the bottom. We are told that the electric field is uniform, as we would expect for a parallel plate capacitor system, and it has a magnitude of 8.0 times 10 to the 4 volts per meter. Now, a proton undergoes a displacement of magnitude d is equal to 0.5 meters. So it starts here at some initial position, and it ends up at this final position here, and it goes in the same direction as E. We want to find the speed of the proton after it completes this displacement. So we can do this in a couple ways, but we're going to go down the energy route because that's what we're talking about in this chapter. So something that you should hopefully remember from Phys 204 is this equation here. This here is for an isolated system. It means the total change in kinetic energy plus the total change in potential energy is equal to 0, right? So that means that our loss of potential energy gets translated to a gain in kinetic energy. The equation that you're going to use in this type of system, and by system I mean where we have a uniform electric field, is going to be this one. But instead of just starting off this equation, I really want to show you where it comes from, so that let's say you forget if you can or can't use this equation, you should just really go back to the basics, which is this equation here, and figure it out from there. So we define delta V here to be the change in potential, and it's defined as the change in potential energy divided by Q. And we know that change in potential energy divided by Q is equal to the negative integral from A to B of E dot ds. Now here, if we look at where our proton's going, ds is this way, and it's in the same direction as E. So this is a dot product here. So we have E dot ds is equal to E ds cos theta. They're in the same direction, so this is going to be equal to 1. That means delta V is equal to negative integral from A to B of E ds. Now, because we have this uniform electric field, we know that E is constant, so we can just take E out, and we get delta V is equal to negative E integral from A to B. Instead of saying ds, we're just going to call it dx. It doesn't really matter. I can call this the positive x direction if I want to. That's just whatever you feel like doing here. And the integral of dx is going to be equal to x that goes from A to B. Now, if I define this to be A, right, and this to be B, well, going from A to B is literally just D. So this, delta V, is equal to negative ED. And that is the equation that we have here when we have a uniform electric field. So now we're going to combine everything we know to actually solve the problem. So we can erase all of this for now and just concentrate on these equations where we have this, and we also have the following equation. Right, so this is linking our change in potential energy to our change in potential. And we just insert delta V here. And from here, we can just plug everything in to figure out what delta U is. But we don't really care about delta U, right? Because the idea is we're trying to figure out the speed. So that involves figuring out what the change in kinetic energy is. So here we can write delta K plus delta UE is equal to 0. So delta K plus, here it's negative QED is equal to 0, meaning delta K is equal to QED. Now we also know that kinetic energy is equal to 1/2 mv squared. So here, this is going to be 1/2 mv final squared minus 1/2 mv initial squared. But remember, our proton started off at rest, meaning its initial velocity is 0. And then this is q ed. All right, so then we have this as our equation. All we have to do is isolate for v. So we have v final is equal to 2qed divided by m square root. I can now plug in all my numbers here, and I get square root of 2 times q is a proton, so 1.6 times 10 to the negative 19 coulombs. E is my electric field, that's given to me. 8 times 10 to the 4 volts. And then I have d, which is how far it went, half a meter. All of this divided by m, which is the mass of a proton, about 1.67 times 10 to the negative 27 kilograms. Take the square root of all of that, and I get about 2.8 times 10 to the 6 meters per second as my answer. All right, here I just added like a little blurb that's kind of describing the situation here. So what I say is that due to the electric field, the proton experiences an electric force in the direction of the field lines. And that's definitely one way we can describe the problem in terms of, well, okay, we have a field, and then because of the field, it experiences an electric force, right? But here in this problem, the way we solved it was by talking about, instead of forces, energy. So we can describe the scenario in terms of energy. A potential field describes how much potential energy a charge would have at each point in space. So a positive charge will naturally move from a point of high potential to low potential. So here, if I were to place a positive charge really, really, really close to this positive area here, it's going to really want to fly away pretty fast because they're just so close. Another one, it's going to feel a large repulsive force. We can talk about that in terms of this area being an area of high potential, and this down here being an area of low potential. Of course, this is due to like the perspective of a positive charge, right? It's the opposite if this were a negative charge. So basically we want to go from an area of high potential, and as we travel this way, we lose potential energy, and it gets converted to kinetic energy, which is this, right? When we lose potential energy, it gets converted to kinetic energy in the form of movement or velocity, and that's how we're able to figure out the velocity due to the energy conservation.